9 minutes. That's how long the protection lasted. 9 minutes from the moment the de-icing crew finished treating the Challenger 650 in Bangor, Maine, to the moment that aircraft rotated for takeoff with contaminated wings that would kill 6 people. 9 minutes during which a carefully formulated chemical mixture, specifically designed to protect aircraft from ice accumulation, was completely overwhelmed by the weather conditions. 9 minutes during which the crew believed they were protected, when in reality their wings were accumulating deadly contamination. Today we need to talk about de-icing fluid. Not in general terms, but in specific technical detail. Because understanding why 6 people died in Bangor on January 25, 2026, requires understanding how de-icing works, what it's designed to do, what its limitations are, and, most critically, how ice pellets can defeat even the most advanced de-icing treatments in a matter of minutes. This is the story of how a protective system failed, how holdover time calculations proved inadequate, and how a phenomenon that the Allegiant crew described as "it stuck to us like there was nothing there" overwhelmed the de-icing treatment that should have kept those wings clean. Let's start with the basics of aircraft de-icing, because most people don't understand how the system works. When an aircraft sits on the ground in winter weather, precipitation falls on it. Snow, freezing rain, sleet, ice pellets. That precipitation can stick to the aircraft surfaces, particularly the wings. Any contamination on the wings is extremely dangerous because it disrupts the airflow and can cause loss of control during takeoff. So before an aircraft can safely depart in winter weather, it must be de-iced. The de-icing process uses specialized fluids that are sprayed onto the aircraft by ground crews using truck-mounted boom systems. There are 4 types of de-icing fluid, creatively named Type 1, Type 2, Type 3, and Type 4. Each has different properties and different uses. Type 1 fluid is a heated mixture of propylene glycol or ethylene glycol and water. The heating is critical because hot fluid is much more effective at melting existing ice and snow. Type 1 is typically colored orange. When it's sprayed on an aircraft, it melts and removes any contamination that's already there. Ice, frost, snow, all of it gets dissolved and washed away by the hot Type 1 fluid. But Type 1 has a problem. It's thin, it's watery. Once it's sprayed on, it doesn't stay on the aircraft surfaces very long. It runs off. And once it's gone, there's nothing protecting the aircraft from new contamination. That's where Type 4 fluid comes in. Type 4 is also a glycol-based mixture, but it has additives that make it much thicker. It's a gel. When it's sprayed on an aircraft, it doesn't run off immediately. It coats the surfaces, particularly the wings, with a thick protective layer. That layer is designed to do 2 things. First, it prevents new precipitation from adhering to the wing surface. Snow that falls on Type 4 fluid sits on top of the fluid rather than sticking to the metal. Second, and this is the clever part, Type 4 fluid is shear thinning. That means when it experiences high-speed airflow during the takeoff roll, it becomes less viscous and flows off the aircraft. By the time you lift off, the airflow has stripped the fluid from the wings, leaving them clean. It's an elegant solution. Apply a protective gel that keeps ice from forming, then have it automatically remove itself during takeoff. Type 4 is typically colored green. So the standard de-icing procedure for an aircraft in winter weather is a 2-step process. First, you spray hot Type 1 fluid to remove existing contamination. Then, you spray Type 4 fluid to protect against new contamination. This is exactly what was done to the Challenger in Bangor. Now here's where it gets complicated. Type 4 fluid doesn't last forever. It has what's called a holdover time. Holdover time is the estimated time that the fluid will continue to provide protection against ice accumulation under specific weather conditions. And this is critical. Holdover time is not a guarantee. It's an estimate. It depends on weather conditions, temperature, type of precipitation, intensity of precipitation. All of these factors affect how long the fluid remains effective. The FAA publishes holdover timetables that give pilots guidance on how long they can expect protection in different conditions. For example, in light snow at -5 Celsius, Type 4 fluid might have a holdover time of 20 to 30 minutes. In freezing drizzle at -10 Celsius, it might only be 10 to 15 minutes. The colder it is, the shorter the holdover time. The heavier the precipitation, the shorter the holdover time. And here's the important part. These are laboratory-tested estimates. They're based on controlled conditions. Real-world conditions can vary dramatically. The holdover timetables published by the FAA and the manufacturers assume continuous precipitation of a specific type. But weather doesn't work that way. Weather is variable. Weather has bursts. Weather has pockets. You might have light snow for 10 minutes, then a burst of heavy snow for 2 minutes, then light snow again. Or you might have snow mixed with ice pellets. Or you might have localized areas where precipitation is heavier. All of these variations can dramatically reduce the effective holdover time below what the tables predict. And this is where the system starts to break down. Because pilots are making decisions based on holdover timetables that assume uniform conditions. But the actual conditions they're operating in may be far more severe than the tables account for. Let's talk about what happened in Bangor. The Challenger arrived at approximately 6:09 p.m. from Houston. The aircraft sat on the ground for over an hour and a half. During that time, the temperature was below 3 degrees Fahrenheit. That's -16 Celsius. Extremely cold. The aircraft's metal surfaces were cold-soaked. That means they had taken on the temperature of the ambient air. When metal is that cold, any moisture that contacts it freezes instantly. You can't just have cold metal surfaces in winter. You essentially have refrigerated surfaces. Around 7:20 or 7:30 p.m., the pilot taxied to the de-icing pad. The aircraft was treated with both Type 1 and Type 4 fluids. The de-icing crew sprayed hot Type 1 to remove any frost or ice that had accumulated during the hour and a half on the ground. Then they applied Type 4 to protect against new accumulation. This treatment probably took 5 to 10 minutes to complete. Let's say it was completed at 7:30 p.m. The aircraft then remained at the de-icing pad for approximately 20 minutes. Why would they sit at the de-icing pad for 20 minutes? Several possible reasons. Maybe they were coordinating with the passengers. Maybe they were completing paperwork. Maybe they were running checklists. Maybe they were waiting for clearance to taxi. Whatever the reason, they sat there for 20 minutes while snow and ice pellets fell on their aircraft. At approximately 7:50 p.m., they taxied from the de-icing pad to runway 33. That taxi probably took another 5 to 10 minutes. And then they were cleared for takeoff at approximately 7:55 p.m. So let's do the math. De-icing completed at 7:30, takeoff at 7:55. That's 25 minutes. Now let's look at what the holdover timetables would have predicted for the conditions that night. The official weather report was light snow, temperature -1 Celsius, which is what the tower was broadcasting. But we know from the Allegiant crew and from the Ring doorbell audio that ice pellets were falling, not just snow. Ice pellets dramatically reduce holdover time. For Type 4 fluid in light snow at -1 Celsius, the holdover timetable gives a range of approximately 15 to 30 minutes. But that's for continuous light snow. For ice pellets or freezing drizzle mixed with snow, the holdover time can be as low as 5 to 10 minutes. And remember, these are estimates. They're not guarantees. So the Challenger crew, if they consulted the holdover timetables, would have seen that they were within the estimated protection window for light snow. 25 minutes is within the 15 to 30 minute range. They probably thought they were fine. But the actual conditions were not light snow. They were ice pellets mixed with snow. And the holdover time for those conditions was much shorter, possibly as short as 10 minutes, which means by the time they taxied to the runway, by the time they received takeoff clearance, by the time they began their takeoff roll, Their wings were already contaminated. The Type 4 fluid had been overwhelmed. Ice was adhering to the wing surfaces underneath the fluid layer, and they didn't know it. Let's talk about how ice pellets defeat Type 4 fluid, because this is the technical heart of why this accident happened. Type 4 fluid is designed to create a barrier between the wing surface and precipitation. When snow falls on Type 4 fluid, the snow sits on top of the gel. The glycol in the fluid depresses the freezing point, so the interface between the snow and the fluid doesn't freeze solid. As more snow accumulates, the weight and the shearing action cause the fluid to slowly flow, carrying the snow with it and keeping the wing surface underneath clean. This works well for snow because snow is light and fluffy. It doesn't have much mass. It doesn't penetrate the fluid layer. But ice pellets are different. Ice pellets are solid. They're dense. They have mass. When an ice pellet falls and hits Type 4 fluid, it doesn't just sit on top. It penetrates. It pushes through the gel layer. And because ice pellets are already frozen solid, they don't get dissolved by the glycol. They reach the metal wing surface and stick there. Because the wing surface is -16°C, well below freezing, the ice pellet bonds to the metal instantly. Now imagine thousands of ice pellets falling over a 20-minute period, each one penetrating the Type 4 fluid, each one bonding to the wing surface. You're building up a layer of ice contamination underneath the protective fluid layer. And from the outside, you can't see it. The wing is still covered with green Type 4 fluid. It looks protected, but underneath that fluid, there's a layer of ice. And that ice is exactly the kind of contamination that disrupts airflow and causes stall. This is what the Allegiant pilot was describing when he said it stuck to us like there was nothing there. The ice pellets were penetrating the de-icing fluid and contaminating the wings as if the fluid wasn't even present. The protective system had been defeated. Now let's talk about the holdover timetables and why they failed to predict this. The holdover timetables are developed through laboratory testing. Manufacturers spray fluid on test surfaces, expose them to various types of precipitation at various temperatures, and measure how long it takes for contamination to accumulate. They publish these results as tables that pilots can reference. But the testing has limitations. First, it's done in controlled conditions. Uniform precipitation, steady temperature, no wind. Real-world conditions are messier. Second, the tables are conservative in some ways and optimistic in others. They're conservative in that they give you a range, and you're supposed to use the lower end of the range for safety. But they're optimistic in that they assume you'll conduct a pre-contamination check before takeoff. The idea is that holdover time tells you how long you probably have, but you're supposed to verify your wings are clean before you actually take off. The problem is that pre-contamination checks have their own limitations. How do you check for ice underneath a layer of Type 4 fluid? If you're looking out the window from the cabin, you're seeing green fluid. You're not seeing the metal underneath. If you go outside and physically touch the wing, you're feeling fluid, not metal. You'd have to wipe away the fluid to actually check the surface, and that's not practical or safe to do on an active ramp in a snowstorm. So pilots end up relying on the holdover timetables. If they're within the published time, they assume they're protected, and usually they are, but not always. And in this case, they weren't. There's another factor that made this worse. The aircraft sat at the de-icing pad for 20 minutes. During that time, they were stationary. No airflow over the wings, no movement, just sitting there while precipitation fell. That's the worst case scenario for holdover time, because the fluid isn't being sheared, isn't being agitated, isn't flowing. It's just sitting there taking hits from ice pellets. If they had taxied immediately after de-icing, if they had kept moving, the holdover time might have been slightly longer. But they sat, and while they sat, their protection eroded. By the time they finally taxied to the runway, the Type 4 fluid had already been compromised. It was still there, it was still coating the wings, but it was no longer preventing ice from adhering to the metal surfaces underneath. Now let's talk about what should have happened. The proper procedure, the procedure that would have saved 6 lives, is to conduct a thorough pre-contamination check before taking the active runway. In some operations, particularly airlines, this is done by the pilot going back into the cabin and visually inspecting the wings from the passenger windows. You're looking for any signs of contamination, roughness, irregularities, anything that looks like ice or frost. In other operations, particularly in severe conditions, ground crew can conduct a tactile check. They physically touch the wing surface to feel for contamination. This is more reliable than visual inspection, but it requires accessing the wing, which isn't always possible or safe. The Allegiant crew conducted this check. They found contamination. They refused to take off. They made the right call. They probably saved 100 lives by refusing to take off with contaminated wings. The Challenger crew, as far as we know, did not conduct a thorough contamination check. Or if they did, they didn't detect the contamination that was present. It's possible they looked out the window and saw green fluid and assumed that meant they were protected. It's possible they were relying on the holdover timetables and believed they were still within the safe window. It's possible they were feeling time pressure to get going and didn't want to delay further by going back for another de-icing treatment. We don't know their reasoning. The cockpit voice recorder may provide answers, but what we know is that they took off with contaminated wings, and that contamination killed them. Here's the broader systemic problem. The holdover time system assumes that pilots can accurately assess their situation and make good decisions about whether they're still protected. But that assumption breaks down when the weather conditions don't match the published tables. Ice pellets aren't explicitly covered in many holdover timetables because they're relatively rare. They fall between freezing rain and snow in terms of how they behave. Some tables lump them in with freezing drizzle. Others don't mention them at all. So a pilot encountering ice pellets might not have clear guidance on what holdover time to use. They might default to the snow values, and they'd be wrong. Ice pellets have dramatically shorter holdover times than snow. But if you don't know that, if you haven't been trained on that, if it's not in your tables, you're operating blind. The NTSB investigated this exact issue after the Montrose Challenger crash in 2004. They found that holdover time guidance was inadequate for mixed precipitation conditions. They recommended that the FAA improve the tables and provide better training to pilots on how to assess holdover time in variable conditions. The FAA made some improvements. They expanded the tables, they added more precipitation types, they created training materials, but the fundamental problem remains. Holdover time is an estimate, not a guarantee. And in conditions that don't match the table assumptions, that estimate can be dangerously optimistic. The system relies on pilot judgment, and pilot judgment relies on accurate information. When the tower is saying light snow, but the reality is ice pellets, when the holdover tables say 20 to 30 minutes, but the actual protection is 10 minutes, when the visual appearance of the wing suggests it's protected, but contamination is present underneath the fluid, pilot judgment fails. Not because the pilots are incompetent, but because the information they're basing their decisions on is incomplete or inaccurate. Let's talk about what happens to that Type 4 fluid during the takeoff roll, because this is important for understanding why contamination under the fluid is so dangerous. As the aircraft accelerates, the airflow over the wings increases. At around 60 or 70 knots, the shearing force becomes strong enough to start removing the Type 4 fluid from the wings. It flows backward, off the trailing edge. By the time you reach rotation speed, most of the fluid has been stripped away. This is by design. You want the fluid to protect you during taxi and the early part of takeoff, then get out of the way so it doesn't add weight or disrupt the airflow during flight. But here's the problem. If there's ice contamination underneath the fluid, when the fluid gets stripped away during the takeoff roll, that ice contamination is suddenly exposed. And it's exposed at the exact moment when you need clean wings most. At rotation, when you're pulling back on the yoke and increasing angle of attack, you need maximum lift. If your wings have ice contamination, one wing might stall. And if one wing stalls at 50 feet altitude during rotation, you're dead. This is likely what happened to the Challenger in Bangor. They accelerated. The Type 4 fluid was stripped away during the roll. The ice contamination that had accumulated underneath the fluid during those 25 minutes was exposed. They rotated. The angle of attack increased, and one wing, probably the left wing based on how these accidents typically develop, reached its contaminated stall angle of attack. The wing stalled. The aircraft rolled. It flipped inverted. It crashed. 45 seconds from takeoff clearance to impact, all because the protective system that was supposed to keep their wings clean had been overwhelmed by ice pellets in 9 minutes. Not 25 minutes, 9 minutes. Because that's probably when the ice pellets overwhelmed the Type 4 fluid, the first 9 minutes after de-icing. Everything after that was just accumulating more contamination on top of what was already there. The Allegiant crew figured this out. They spent time at the end of the runway. They probably sat there for a few minutes running checks, coordinating, preparing for departure. And during those few minutes, they got hit by ice pellets. They conducted their contamination check and found ice on their wings. They made the call to refuse the takeoff. That decision was based on direct observation. They felt the contamination or saw it. They didn't rely on holdover timetables. They relied on their own eyes and hands. And that saved them. The Challenger crew didn't make that check or didn't detect the contamination. They relied on the holdover timetables. They relied on the fact that they were still within the published window. They relied on the visual appearance of Type 4 fluid on their wings, and they were wrong, and it killed them. Here's what needs to change. First, holdover timetables need to explicitly address ice pellets as a distinct precipitation type with dramatically reduced protection times. Pilots need to know that ice pellets are not the same as snow, that they penetrate Type 4 fluid, that they can contaminate wings in a fraction of the time that snow would. Second, pilots need better training on conducting pre-contamination checks in conditions where visual inspection is inadequate. If your wings are covered with Type 4 fluid, you can't see the metal surface. You need tactile checks or other methods. Third, the weather observation and reporting system needs to be more accurate about precipitation type. The tower was reporting light snow when ice pellets were falling. That misinformation directly contributed to the accident. Pilots were making decisions based on incorrect weather reports. Fourth, there needs to be a cultural shift toward extreme conservatism with holdover times. If you're anywhere close to the published limit, go back for another treatment. If there's any doubt, delay the departure. If other aircraft are refusing to take off, find out why before you go. The technology exists to solve some of these problems. There are sensors that can detect wing contamination in real time. They measure the surface roughness or use other methods to determine if ice is present. Some aircraft have them installed, but they're expensive and they're not required on most business jets. The regulatory framework exists. The FAA has clear rules about contaminated wing surfaces, but enforcement is difficult because the determination of whether a wing is contaminated relies on pilot judgment. And pilot judgment can be wrong, especially when the information environment is misleading. The training exists. Every professional pilot goes through winter operations training, but training in a classroom is different from making a split-second decision on a dark, snowy ramp with passengers waiting and schedules slipping. 6 people died in Bangor because de-icing fluid failed. It didn't fail because it was defective. It didn't fail because it was applied incorrectly. It failed because ice pellets overwhelmed its protective capability in less time than the holdover timetables predicted. It failed because the weather conditions were more severe than reported. It failed because the crew didn't detect the contamination that had accumulated underneath the fluid layer. It failed because the system assumes perfect information and perfect decision-making, and neither exists in the real world. Type 4 fluid is an amazing technology. It saves countless flights every winter, but it's not magic. It has limits. And when those limits are exceeded, when ice pellets penetrate the protective layer, when holdover time is shorter than predicted, when pilots don't detect the contamination, the protection fails, and people die. That's what happened in Bangor. 9 minutes from de-icing to contamination, 25 minutes from de-icing to takeoff, 45 seconds from takeoff clearance to crash. The numbers tell the story. The de-icing fluid failed, and 6 people paid the price.